In this video, we will be solving a scheduling problem by critical path algorithm. And first step in using the critical path algorithm is to find all the critical times as indicated using the backflow algorithm. So that's what we did in the last video. So in this particular example, which was putting together a drawer from IKEA, and we wanted to know how long it would take, we first found all the critical times, so that's step one when using critical path algorithm. Step two is to create the priority list. So kind of like how in the decreasing time priority algorithm, we made a priority list based on the times. But when we're using the critical path algorithm, it says using the critical times obtained in step one, create a priority list with the tasks listed in decreasing order of critical time. So it's almost exactly the same. Instead of listing the tasks in decreasing order of processing time, we're going to use a decreasing order of critical time instead. So basically, instead of listing them in order of their numbers in parentheses, we're going to change that to their brackets, where the highest bracketed numbers would be highest priority and the lowest bracketed numbers would be lowest priority. And this makes actually really good sense because the tasks with the longest critical times, as we talked about, are going to have the longest times of completion from that specific point. So like, for example, AP had a critical time of 34. That had the longest chain of events. So it makes sense that we'd want to get those done first because there's more that needs to get done after this. And we want to be able to allow that chain to finish as quickly as possible by focusing on the highest critical times first. And with a lot of those other tasks, same deal. Like AF having a high critical time also means from there it's going to take that long. So the critical path algorithm makes really good use of knowing the critical times of each of the vertices, and it makes sense to try to do the longest ones first. And then the last step is to create a schedule. So once we have the priority list, just like we've been doing in all the other problems, we're ready to go. So let's go ahead and get into it. So in this one, we first need to create a priority list, which will be just a list of the of each vertex in order of its critical time. So AP is going to come first. Let me move this right there. AF had the next highest critical time. Then AW is 28. IF is 27. IW is 22, and so on. AD is 18. IP is 15. Looks like we have two 11s. In any case, if there is a tie, what I recommend is prioritizing the task which is on the critical path first. But again, they would technically be equal in priority, but I'm going to go ahead and list HU ahead of PL. Then ID is 10. Next up is IC is 7. FW is 6. PU is 5. PD is 3. And EU is 2. And that should do it. Again, we want to make sure we have all the tasks. Might be a good idea to count your tasks to make sure you have them all. We have 4, 7, 8, 9, 10, 12, 15, assuming I didn't miss any. And so that would make 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Cool. Good to go. And then now I have my priority list. I have my digraph. So I should be ready to schedule this. And it says use it to schedule the project with 2 assemblers. So let's assume that myself and my buddy are going to put together this dresser. And want to know how long it's going to take us to do all these tasks in the prerequisite order. The critical path algorithm should generate us a very good priority list and greatly minimize the amount of idle time. This is also going to be a lot better than the decreasing time priority list because it will, and you'll see as we run through the example, it tends to organize the tasks in an order you're ready to do them. Because as we look at the digraph, we can tell that the larger numbers are up front, and those are the tasks we have to do first anyway, so it just kind of makes sense in terms of actually scheduling it. We're going to have these ones naturally be higher in the priority list, and they're going to be scheduled first. But as usual, we have in this graph, we have 4 ready tasks from the beginning. We have AP, AF, AW, and AD. So go ahead and circle those AP, AF, AW, and AD. And we're always going to schedule the first ready tasks on any available processor. So AP is going to go first on processor 1. So let's say processor 1 is me, processor 2 is my friend. I will be doing task AP first. And also, just a thing to be careful about is you want to make sure you're using the processing time when you're scheduling tasks, not the critical time. Because the critical time is not how long it takes, it's the total time, and that's not what we're doing, right? So AP still is going to take 7 minutes to do. So when I'm scheduling it, I want to make sure to still use the parentheses numbers, not the bracket numbers. And there's so many numbers at this point that we found on the critical times that it's really easy to accidentally mess that up. And meanwhile, processor 2, aka my friend, will work on the next task AF. And AF has a processing time of 5, so that's going to come next. And it might be a good idea to note the processing times on your priority list, but it's important that we use the critical, that we're using the digraph at the same time. Let me see if I can get this in a position where I can actually see both of them so I don't have to keep scrolling up and down as you're watching this. And that should be good enough, I think. Okay, then once AF is completed, so my buddy is going to be finished with his task first. So, and again, if I mark the digraph, it can kind of help me figure out what's going on. But once AF is completed, notice that IF is not quite ready yet, and it's not high in the priority list. So really, AW is next in priority list. It's ready to go. So that's what's going to happen next. AW, which is going to take 6 minutes. So and also again, since my buddy's done with his task first, we're always gonna schedule whatever task is ready on the first available processor from left to right. So he's gonna finish first, and that's usually how it will work, though not always. So usually the second processor becomes ready before the first. Well, when you're using the decreasing time priority list, that's almost always going to happen, but that happens fairly frequently. Anyways, now after 7 minutes, I have finished my task AP, and now I'm ready for something to be scheduled on mine. And AEW is in progress. Also, I could skip ahead to AD, but what I would typically do is check to see, well, are these tasks ready? Because those are technically higher priority. I'd want to do those first ahead of AD if at all possible. So that's why in each step I recommend checking. And notice that after 7 minutes, I would also be done with AP, and IF would become ready. So let me go ahead and mark that. Because after 7 minutes, I already finished that. So now this becomes ready. And that's why, and we have also finished AW. So I'm going to cross that out also. But that's why I strongly recommend after any time you schedule any task, always check, see, is anything new ready? Because in that case, it is. IF should be what happens next because it's higher priority than AD. And IF is going to take 5 minutes. I apologize if this video is a little bit hard to follow. I am quite tired right now. So I'm just trying to finish this up. Let me move this up ever so slightly. Okay, and then I'll be done with I'll work on IF. Then my buddy will finish AW after 11 minutes. Notice that IW at this point in time, IW will not quite be ready yet because notice I'm still working on IF after 11 minutes. I won't be finished until 12 minutes. So now is when we're going to skip ahead to AD because AD is ready to fire and we don't want my buddy sitting there doing nothing. Well, he might be happy with that, but we're trying to get it done as quickly as we both possibly can. AD should be 19 minutes. He'll be in progress. And then now after 12 minutes, if I'm trying to figure out what I'm going to schedule right here, now IF is completed and IW is now ready because both AW and IF have been completed. So now we're ready to go. IW would be next. And IW is going to take 7 minutes, and actually that will conveniently put me at 19 minutes. So both of us will finish our tasks at the same time, and we can move on. Now let me move back up to the graph, and it can be helpful to mark off the tasks that have been completed on your digraph. That way you can get a sense of, well, what's next. Well, now PL, IP, and ID are all ready because every prerequisite is now done for those three simultaneously. So I can go ahead and circle those PL, IP. Where's IP? I can't see it on my tablet. There we go. IP, PL, and ID already. And we can see that IP is the highest priority. I mean, you could also see, but just by looking at the digraph, you don't necessarily need to write out the full critical time priority list. But if you just make a rule that you're always going to do the highest available ready task, you can kind of see just always pick the biggest number from the digraph. But it's helpful to have a list to follow along with. Okay, so IP will be scheduled on processor 1. IP has a time of 4 minutes. Meanwhile, processor 2 can work on PL. HU is not ready until IP is done, so that's not an option. And PL, thankfully, also takes 4 minutes, so that will actually also coincide exactly with IP. Another 4 minutes there. And we'll both finish those tasks after 23 minutes. And now we'll both finish. And now at this point in time, HU will become ready because its only prerequisite task was IP. And again, since that's higher priority, I want to definitely do that before I do ID, even though ID was ready before. It doesn't really matter who's ready before. It just matters who's the highest priority, which task is the highest priority, and which one is actually ready. So HU is ready. That will take another 4 minutes, which will be scheduled on processor 1. Meanwhile, processor 2 can work on ID, which is the next task, and it's also ready, so that's good. ID takes 5 minutes. That will go a little longer. Putting him right there at 28 minutes. Then once HU is completed, ID will be in progress. After 27 minutes, we could check to see what is ready. But once HU is done, note that PL is also done, so IC becomes ready. But PD is also ready because HU has been completed. But EU is not ready because it has to wait for PU and ID to finish. And I'll go ahead and mark these. You know, it's helpful to mark these off as I'm going, but unfortunately my tablet is not showing everything at once, so I have to keep scrolling up and down. But I can kind of get a picture of what is ready. That might be something that's hard to follow on this video, because it's, you know, kind of hard to explain, but I can kind of X off everything to see, okay, well, what is actually ready? Those are both ready because everything in before them in the arrows before them has all been completed, whereas ID is not. And this is, you know, currently in progress. Anyways, I'm going to go ahead and do IC next because, again, it's the next highest priority task, so that always makes it easier when it is high priority and it's ready to go. IC only takes 1 minute, so that would put me right there. IC would also leave me right at 28. Make that a little bit better. And then IC will be done, and FW will become ready as well. So FW is now ready, and at 28 minutes, actually also PU will become ready because processor 2 has now finished with ID. And so I'll schedule FW first because that's highest priority and it's ready because its prerequisite IC has just been completed. So FW, and this is just the thing I warn you to be careful about. If it's kind of difficult to follow, there's so many steps in here. Just what you always want to consider is, well, what's highest priority and is it actually ready? Has everything that needs to be done been actually completed? If so, that's always the choice. FW is highest priority. PU is next highest priority, and it's also ready. PU will finish first. Meanwhile, PD is next up. It's ready. So processor 2 can then work on PD, which is another 3 minutes, which will put him at 34 minutes. And that will line up with me completely, and I will finish FW right when he finishes PD. And then the last task is EU, which is just 2 minutes, which technically it doesn't matter because both of us are available and that's it, but we always schedule it on the first available processor. So I'll go ahead and do that myself instead of making my buddy do it, which would leave 2 minutes of idle time for him. And anyways, this now is what we're looking for. Again, you could be asked to find the schedule itself, or a lot of times you'll be asked for what is the finishing time of the project. But there is a there is a correct answer, and everybody's priority list when you're working on these problems should look the same, as should your schedule, because it's a definitive process. If you're doing it right, it should come out the exact same way. But it's very easy to accidentally schedule a task in the wrong spot. It's easy to accidentally overlook, okay, is this task ready or not, and miss those things. And it's definitely going to take a lot of time. And since this is all online, I guarantee you guys this will be a little bit frustrating to practice. But just keep practicing. On the test, I'm not necessarily expecting for perfection, but you can always turn back to 8.3, which is on how do I actually follow the rules, and read through it if you're just feeling hopelessly frustrated with this. And I'll do another example of using the critical path algorithm in the next video just to give you a couple more practices.